The core of real analysis involves mathematically guaranteeing strict order and absolute predictability within seemingly chaotic, infinite systems. Early calculus methods rely on explicit evaluation. To find the limit of a sequence, you compute its exact numerical boundaries through algebra. This graph illustrates the squeeze theorem. We evaluate a difficult sequence, like the sine of n over n, by trapping it between two known simpler functions, sandwiching it as it approaches zero. This method has a significant limitation. The squeeze theorem requires external, explicitly known bounding functions to act as the exact boundaries of the sequence. When sequences are generated by internal, self-referential rules without obvious external boundaries, traditional algebraic squeezing methods fail to provide a solution. This problem is most evident in recursive sequences. Here, each term is generated strictly based on the value of the term immediately preceding it. This plot shows a specific recursive sequence. X sub n plus 1 equals the square root of 2 times x sub n, starting with x sub 1 equal to the square root of 2. Because of its recursive nature, no obvious upper function curves exist to squeeze the sequence against. We must find a way to prove this sequence converges by examining only its internal behavior, rather than searching for an external comparison. This requires us to shift away from algebraic tricks and rely instead on the structural axioms of the real number line itself. The first requirement is monotonicity. A sequence is monotonic if it consistently increases or consistently decreases, never reversing its direction. The Monotone Convergence Theorem, or MCT, is the tool that bridges this internal behavior with convergence. This chart shows the geometric intuition of an increasing monotonic sequence. If this increasing sequence is bounded above, meaning it cannot cross a specific ceiling, its inability to decrease forces it to compress as it advances. The completeness of the real numbers ensures that this sequence will hit a limit called the supremum, or the least upper bound. The MCT guarantees that a limit exists purely based on bounded monotonic behavior. This allows us to prove a sequence converges without needing the exact limit value in advance. We return to our recursive sequence. X sub n plus 1 equals the square root of 2 times x sub n. This handwritten proof addresses the sequence using logical induction rather than direct algebra. Induction confirms the first condition. The sequence is strictly bounded between 0 and 2. It also confirms the second condition. The sequence is strictly monotonically increasing. Since the sequence is both bounded and monotonic, the Monotone Convergence Theorem allows us to mathematically guarantee that a limit exists. Now that existence is proven, we can substitute L into the sequence formula to solve for the exact value algebraically. Here, the limit is 2. This step is the logical requirement for the calculation. By proving existence implicitly first, we establish the mathematical validity needed to use standard algebra to find the exact limit. This logic leads to a new question. What happens if a sequence is bounded but lacks monotonicity? This scatter plot shows the erratic distribution of the sequence sine of n. It oscillates between 1 and -1 without converging. We can still find order by selecting specific indices to form a subsequence. By discarding most of the points, we isolate a subset that behaves monotonicity. The monotone subsequence theorem states that every real sequence contains a monotone subsequence. This is verified using the peaks proof. A geometric peak is a point that is higher than every point that follows it to the right. If a sequence has infinitely many peaks, connecting them creates a strictly decreasing monotone subsequence. If there are only finite peaks, then past the last peak, every point must be followed by at least one higher point, allowing us to build an increasing subsequence. The peaks proof confirms randomness within a bounded sequence is never absolute. Even in erratic distributions, a monotonic trajectory remains mathematically accessible. These concepts converge in the Bolzano-Weierstrass Theorem. First, the monotone subsequence theorem ensures we can extract a monotonic thread from any bounded sequence. We apply the peaks logic to the chaotic data, isolating that subset. Since the original sequence was bounded, our extracted monotonic thread is trapped by those same bounds. Because this thread is both monotone and bounded, the Monotone Convergence Theorem dictates that it must converge. This theorem states that every bounded sequence in real space contains a convergent subsequence. The Bolzano-Weierstrass theorem ensures that convergence is a property of any bounded sequence. By proving a limit point exists regardless of complexity, this theorem provides the rigorous framework to analyze systems where explicit calculations are impossible.